Welcome to the session Two-Dimensional Heat Equation and Wave Equation. Two-dimensional heat flow. Consider the flow of heat in a metal plate in the x or y plane. If the temperature at any point is independent of the z coordinate and depends on x, y and t only, then the flow is called two-dimensional and the heat flow lies in the plane x or y only and is zero along the normal to the plane x or y. Take a regular element of the plate with sides delta x and delta y and thickness alpha. Then the quantity of heat that enters the plate per second from the sides AB and AD is given by minus k alpha delta x into dou u by dou y at y and minus k alpha delta y into dou u by dou x at x respectively, and that which flows out through the sides CD and BC per second is minus k alpha delta x into dou u by dou y at y plus delta y and minus k alpha into delta y into dou u by dou x at x plus delta x respectively. Therefore, the total gain of heat by the rectangular plate ABCD per second is equal to minus k alpha delta x into dou u by dou y at y minus k alpha into delta y into dou u by dou x at x plus k alpha into delta x into dou u by dou y at y plus delta y plus k alpha into delta y into dou u by dou x at x plus delta x, which is equal to k alpha into delta x into delta y into dou u by dou x at x plus delta x minus dou u by dou x at x all divided by delta x plus dou u by dou y at y plus delta y minus dou u by dou y at y all divided by delta y. But the rate of gain heat by the plate is also given by S into rho into delta x into delta y into dou u by dou t, where S is equal to specific heat and rho is equal to density of the metal plate. Therefore, we have k alpha into delta x into delta y into dou u by dou x at x plus delta x minus dou u by dou x at x all divided by delta x plus dou u by dou y at y plus delta y minus dou u by dou y at y all divided by delta y is equal to S into rho into delta x into delta y into dou u by dou t. Dividing both sides by alpha into delta x into delta y and taking the limit as delta x tends to 0, delta y tends to 0, we get k into dou square u by dou x square plus dou square u by dou y square is equal to S into rho into dou u by dou t, or c square into dou square u by dou x square plus dou square u by dou y square is equal to dou u by dou t, where c square is equal to k by s rho. Let it be equation number 3. Equation 3 gives the temperature distribution in the transient state. In the steady state, u is independent of t, so that dou u by dou t is equal to 0, and the above equation reduces to dou square u by dou x square plus dou square u by dou y square is equal to 0, which is known as Laplace equation in two dimensions. Similarly, the equation of heat flow in a solid can be derived as c square into dou square u by dou x square plus dou square u by dou y square plus dou square u by dou z square is equal to dou u by dou t. In the steady state, it reduces to dou square u by dou x square plus dou square u by dou y square plus dou square u by dou z square is equal to 0, which is known as Laplace equation in three dimensions. Note: Laplace equation has wide applications in physics and engineering. The theory of its solutions is called the potential theory, and its solutions are called harmonic functions. The solution of Laplace equation subject to certain boundary conditions is simplified by a proper choice of coordinate system. If the problem involves rectangular boundaries, we prefer to take Laplace equation in Cartesian coordinates given by dou square u by dou x square plus dou square u by dou y square is equal to 0. If the problem involves circular boundaries, we prefer to take Laplace equation in polar coordinates given by dou square u by dou r square plus 1 by r into dou u by dou r plus 1 by r square into dou square u by dou theta square is equal to 0. This equation can be obtained from above by putting x is equal to r cos theta, y is equal to r sin theta, thus changing the independent variables from x, y to r theta. If the problem involves cylindrical boundaries, we prefer to take Laplace equation in cylindrical coordinates given by dou square u by dou r square plus 1 by r into dou u by dou r plus 1 by r square into dou square u by dou theta square plus dou square u by dou z square is equal to 0. This equation can be obtained from Laplace equation in 3 dimensions by putting x is equal to r cos theta, y is equal to r sin theta, z equal to z, thus changing the independent variables from x, y, z to r theta z. If the problem involves spherical boundaries, we prefer to take Laplace equation in spherical coordinates given by dou square u by dou r square plus 2 by r into dou u by dou r plus 1 by r square into dou square u by dou theta square plus cot theta by r into dou u by dou theta plus 1 by r square sin square theta into dou square u by dou phi square is equal to 0. This equation can be obtained from Laplace equation in 3 dimensions by putting x is equal to r sin theta cos phi, y is equal to r sin theta sin phi, and z is equal to r cos theta, thus changing the independent variables from x, y, z to r theta phi. Solution of Laplace equation in 2-dimensional Cartesian form. Laplace equation in 2 dimensions is dou square u by dou x square plus dou square u by dou y square is equal to 0. Let it be equation number 1. Let u is equal to capital X into capital Y, let it be equation number 2, where capital X is a function of small x alone and capital Y is a function of small y alone, be a solution of equation 1. Then dou square u by dou x square is equal to x double dash y and dou square u by dou y square is equal to x y double dash. Substituting in equation 1 we get x double dash y plus x y double dash is equal to 0, or x double dash by x is equal to negative of y double dash by y. Now the left hand side is a function of x only and the right hand side is a function of y only. Since x and y are independent variables, this equation can hold only when both sides reduces to a constant, say k. Then equation 3 leads to the ordinary differential equations d square x by dx square minus kx is equal to 0 and d square y by dy square minus ky is equal to 0. Solving these equations we get, first one, when k is positive and is equal to p square, say capital X is equal to c1 into e raised to px plus c2 into e raised to minus px, and capital Y is equal to c3 into cos py plus c4 into sin py. 2. When k is negative and is equal to minus p square, say capital X is equal to c1 cos px plus c2 sin px, and capital Y is equal to c3 e raised to py plus c4 e raised to minus py. 3. When k is equal to 0, capital X is equal to c1x plus c2 and capital Y is equal to c3y plus c4. Thus the various possible solutions of Laplace equation are u is equal to c1 e raised to px plus c2 e raised to minus px into c3 cos py plus c4 sin py. U is equal to c1 cos px plus c2 sin px into c3 e raised to py plus c4 e raised to minus py. U is equal to c1x plus c2 into c3y plus c4. Of these 3 possible solutions, we have to choose that solution which is consistent with the physical nature of the problem and the given boundary conditions. Example: solve dou square u by dou x square plus dou square u by dou y square is equal to 0, which satisfies the conditions u of 0 y is equal to u of ly is equal to u of x0 is equal to 0 and u of xa is equal to sin n pi x by L. Solution: the given equation is dou square u by dou x square plus dou square u by dou y square is equal to 0. The 3 possible solutions of equation are u is equal to c1 e raised to px plus c2 e raised to minus px into c3 cos py plus c4 sin py, u is equal to c1 cos px plus c2 sin px into c3 e raised to py plus c4 e raised to minus py, and u is equal to c1x plus c2 into c3y plus c4. But the solution satisfying the given conditions is u of xy is equal to c1 cos px plus c2 sin px into c3 e raised to py plus c4 e raised to minus py. Now u of 0y is equal to 0 implies c1 into c3 e raised to py plus c4 e raised to minus py is equal to 0, which implies c1 is equal to 0. Therefore, the solution becomes u of xy is equal to c2 sin px into c3 e raised to py plus c4 e raised to minus py. Since u of ly is equal to 0, we have 0 is equal to c2 sin pl into c3 e raised to py plus c4 e raised to minus py, which implies sin pl is equal to 0, that is pl is equal to n pi, or p is equal to n pi by l, n being an integer. Also, u of x0 is equal to 0 gives 0 is equal to c2 into sin n pi by l into c3 plus c4, which implies c3 plus c4 is equal to 0, that is c4 is equal to minus c3. Therefore, we have u of xy is equal to c2 sin n pi by l into c3 e raised to n pi y by l minus c3 e raised to minus n pi y by l. Replacing c2 c3 by bn, we get u of xy is equal to bn into sin n pi x by l into e raised to n pi y by l minus e raised to minus n pi y by l, that is equal to 2bn into sin n pi x by l into sin h n pi y by l. Putting y is equal to a, we have u of xa is equal to 2 into bn sin n pi x by l into sin h n pi a by l, that is equal to sin n pi x by l by the given condition, which implies 2bn sin h n pi a by l is equal to 1, which implies bn is equal to 1 divided by 2 sin h n pi a by l. Hence, the required solution is u of xy is equal to sin n pi x by l into sin h n pi y by l all divided by sin h n pi a by l. Vibrating membrane two-dimensional wave equation. We shall now derive the equation for the vibrations of a tightly stretched membrane. Assume that the membrane is uniform and the tension in its per unit length is the same at every point in all directions. Let T be the tension per unit length and m be the mass of the membrane per unit area. Consider the forces on an element delta x into delta y of the membrane. Due to its displacement u perpendicular to the xy plane, the forces T into delta y tangential to the membrane on its opposite edges of length delta y act at angles alpha and beta to the horizontal. So, their vertical component is equal to T delta y into sin beta minus T delta y into sin alpha, which is equal to T delta y into tan beta minus tan alpha approximately, since alpha and beta are small. That is equal to T into delta y into dou u by dou x at x plus delta x minus dou u by dou x at x, that is equal to T into delta y into delta x into dou u by dou x at x plus delta x minus dou u by dou x at x all divided by delta x, that is equal to T into delta x into delta y into dou square u by dou x square up to a first order of approximation. Similarly, the forces T delta x acting on the edges of length delta x have the vertical component T into delta x into delta y into dou square u by dou y square. Hence, the equation of motion of the element is m delta x delta y into dou square u by dou t square is equal to T into dou square u by dou x square plus dou square u by dou y square into delta x into delta y, or dou square u by dou t square is equal to c square into dou square u by dou x square plus dou square u by dou y square, where c square is equal to T by m. This is the wave equation in two dimensions. Solution of the two-dimensional wave equation. The two-dimensional wave equation is dou square u by dou t square is equal to c square into dou square u by dou x square plus dou square u by dou y square. Let u is equal to x into y into t, where x is a function of small x only, y is a function of small y only, and t is a function of small t only, be a solution. Then dou square u by dou t square is equal to x into y into t double dash, dou square u by dou x square is equal to x double dash into y into t, and dou square u by dou y square is equal to x into y double dash into t. Substituting in the wave equation, we get 1 by c square into x into y into t double dash is equal to x double dash into y into t plus x into y double dash into t. Dividing by x into y into t, we get 1 by c square into t double dash by t is equal to x double dash by x plus y double dash by y, which holds only when each member is a constant, since x, y and t are independent. Choosing the constant suitably, we have d square x by dx square plus k square x is equal to 0, d square y by dy square plus l square y is equal to 0, and d square t by dt square plus k square plus l square into c square t is equal to 0. The solutions of these equations are respectively capital X is equal to c1 cos kx plus c2 sin kx, capital Y is equal to c3 cos ly plus c4 sin ly, and capital T is equal to c5 cos square root of k square plus l square into ct plus c6 into sin square root of k square plus l square into ct. Hence, the solution of the two-dimensional wave equation is u of x y t is equal to c1 cos kx plus c2 sin kx into c3 cos ly plus c4 sin ly into c5 cos square root of k square plus l square into ct plus c6 sin square root of k square plus l square into ct. Now, let us suppose that the membrane is rectangular and is stretched between the lines x is equal to 0, x is equal to a, y is equal to 0 and y is equal to b. Then the boundary conditions are, first one, u is equal to 0 when x is equal to 0. Second one, u is equal to 0 when x is equal to a. Third one, u is equal to 0 when y is equal to 0. And fourth one, u is equal to 0 when y is equal to b for all t. Applying the condition 1, we have 0 is equal to c1 into c3 cos ly plus c4 sin ly into c5 cos square root of k square plus l square into ct plus c6 into sin square root of k square plus l square into ct. That is, c1 is equal to 0. Putting c1 is equal to 0 in the solution and applying the condition 2, we get sin ka is equal to 0 or k is equal to m pi by a, where m is an integer. Similarly, applying the conditions 3 and 4, we get c3 is equal to 0 or l is equal to n pi by b, where n is an integer. Therefore, the solution becomes u of x y t is equal to c2 c4 into sin m pi x by a into sin n pi y by b into c5 cos pt plus c6 sin pt, where p is equal to pi into c into square root of m square by a square plus n square by b square. Replacing the arbitrary constant suitably, we can write the general solution as u of x y t is equal to summation m varies from 1 to infinity, summation n varies from 1 to infinity, sin m pi x by a into sin n pi y by b into a mn cos pt plus b mn sin pt. Now, suppose the membrane starts from rest from the initial position, u is equal to f of xy. That is, u of xy0 is equal to f of xy. Then, applying the initial condition, dou u by dou t is equal to 0 when t is equal to 0, we get bmn is equal to 0. Also, using the condition u is equal to f of xy when t is equal to 0, we get f of xy is equal to summation m varies from 1 to infinity, summation n varies from 1 to infinity, a mn sin m pi x by a into sin n pi y by b. This is a double Fourier series. Multiplying both sides by sin m pi x by a into sin n pi y by b and integrating from x is equal to 0 to x is equal to a and y is equal to 0 to y is equal to b, every term on the right except 1 becomes 0. Thus, we get integral from 0 to a, integral from 0 to b, f of xy into sin m pi x by a into sin n pi y by b into dy dx is equal to a into b divided by 4 into a mn. That is, a mn is equal to 4 divided by a into b, integral from 0 to a, integral from 0 to b, f of xy sin m pi x by a into sin n pi y by b dy dx. Hence, the required solution is u of xyt is equal to summation m varies from 1 to infinity, summation n varies from 1 to infinity, a mn sin m pi x by a into sin n pi y by b cos pt, where a mn is as above and p is equal to pi into c into square root of m square by a square plus n square by b square. Example: a tightly stretched unit square membrane starts vibrating from rest and its initial displacement is k into sin 2 pi x into sin pi y. Show that the deflection at any instant is k into sin 2x into x sin pi y cos square root of 5 pi ct. Solution: here we have to solve the equation dou square u by dou t square is equal to c square into dou square u by dou x square plus dou square u by dou y square. With boundary conditions u of 0 y t is equal to u of L y t is equal to u of x 0 t is equal to u of x 1 t is equal to 0, and the initial conditions u of x y 0 is equal to f of x y, which is equal to k into sin 2 pi x into sin pi y. Dou u by dou t is equal to 0 when t is equal to 0. The solution satisfying these conditions is u of x y t is equal to summation m varies from 1 to infinity, summation n varies from 1 to infinity, a mn into sin m pi x into sin n pi y cos pt, where p is equal to pi into c into square root of m square plus n square, since a is equal to b is equal to 1 and a mn is equal to 4 divided by 1 into 1 into integral from 0 to 1, integral from 0 to 1, k into sin 2 pi x into sin pi y into sin m pi x into sin n pi y dy dx, which is equal to 4k into integral from 0 to 1 sin m pi x into sin 2 pi x dx into integral from 0 to 1 sin n pi y into sin pi y dy, which is equal to 0 for m not equal to 2 or n not equal to 1. Therefore, a21 is equal to 4k into 1 by 2 into 1 by 2, that is equal to k, and p is equal to pi into c into square root of 2 square plus 1 square, that is equal to square root of 5 pi c. Hence, the required solution is u of x y t is equal to k into sin 2 pi x into sin pi y into cos square root of 5 pi ct. Let me conclude this session. In this session, we have derived two-dimensional heat equation and wave equation. In the steady state condition, the heat equation is known as Laplace equation. We also discussed the various solutions of these equations. Now, you may try to answer the following questions. First one, derive two-dimensional wave equation. Second one, obtain the solution of Laplace equation by variable separable method. Third one, solve dou square u by dou x square plus dou square u by dou y square is equal to 0 for 0 less than x less than pi, comma 0 less than y less than pi, given that u of 0 y is equal to u of pi y is equal to u of x pi is equal to 0 and u of x 0 is equal to sin square x. Fourth one, a square plate is bounded by the lines x is equal to 0, y is equal to 0, x is equal to 20 and y is equal to 20. Its faces are insulated. The temperature along the upper horizontal edge is given by u of x 20 is equal to x into 20 minus x when 0 less than x less than 20, while other three edges are kept at 0 degrees Celsius. Find the steady state temperature in the plate. Fifth one, derive the two-dimensional wave equation and obtain its solution. Sixth one, find the deflection u of x y t of a square membrane with a is equal to b is equal to c is equal to 1 if the initial velocity is 0 and the initial deflection f of x y is equal to k into sin pi x into sin 2 pi y. For your further study, you may go through the books given here. First one, an elementary course in partial differential equations, second edition by T. Amarnath, Narosa Publishing House, New Delhi, 2003. Second one, Higher Engineering Mathematics by B.V. Ramana, Tata McGraw-Hill Publishing Company, New Delhi, 2007. Third one, Partial Differential Equations and Integral Transforms by T. Veerarajan, Tata McGraw-Hill, New Delhi, 2004. Fourth one, Advanced Engineering Mathematics by Michael D. Greenberg, Pearson's Education Private Limited, Delhi, 2002. Hope that you have enjoyed this session. We will meet again with another topic. Thank you.